Alright, back at it with lesson 8.2. We're going to be talking about parallelograms today and properties of parallelograms that you need to have memorized. So what we're going to do is we're going to start by doing a couple things. We're going to define parallelogram. We're going to talk about an example. What does it look like? Alright, we'll give you a couple examples of that. What do we know about its sides? What do we know about its angles? Its diagonals, and then we'll talk about some other stuff that you should know about parallelograms. Okay, make sure that you have these two sheets. Remember this sheet right here, this quadrilateral study guide for chapter 8. You need to make sure you have this in front of you. We're going to be focusing on just this column here for parallelograms. Alright, this is lesson 8.2. Okay, that column. And then also, you need to make sure you have the sheet that goes along with it so we don't have to write as much out. And that's this one that talks about all the different things that are true that we're going to be discussing. Okay, so make sure you have those two sheets nearby. Alright, so let's start with definition. So I'm actually going to move over to this sheet because this was where I told you to take the notes for this chapter for most of the lessons. Alright, so definition of a parallelogram. A parallelogram by definition is a quadrilateral that has two sets of opposite parallel sides. A quadrilateral with two sets of opposite parallel sides. Okay, so we'll draw an example of that. Okay, kind of our typical parallelogram, something that looks like this. Alright, and I'm going to put some marks on there to show that we have parallel sides. Remember our shaded triangles mean parallel sides. And I'm going to put two marks on the top and the bottom to show that they're parallel, but they're different from the left and right sides. Okay, that's one example. Another example might actually be something like this. Okay, once again I'll put some marks on. So two on the top and bottom, one on the left and the right. Now, some people might say, well, that's a rectangle. Well, it looks like it might be, but that's okay. A rectangle does have two sets of opposite parallel sides, so a rectangle by definition would be a parallelogram. Okay. All right, let's go to the sides. Okay, so we got our sides here. Let's talk about what we know about the sides. So let's go back to our sheet here real quick and let's look at this. Let me get up to sides here. So you'll see that letter A there says opposite sides are parallel. And we have a couple options, two sets or one set. Well, obviously by definition, we have two sets of opposite parallel sides. So to keep this short, remember, we're just going to write this down. A, so letter A is true, and it works for two. And I'm going to put my reason here, and this is by definition. Okay, so A2 by definition. All right. Now let's look at the next thing. Sides. Opposite sides are congruent. Two sets or one set. Well, if we look at it, our examples, it looks like that might be true. So let's see if we can prove that it's true. And we're going to prove that that's true using this picture right here. And you'll notice I have theorem written up here, so evidently it must be true. But let's go ahead and prove that the opposite sides of a parallelogram must be true. So go ahead and get this copied down if you want to. We're going to draw a little bit on this. I'm not going to do a full proof where we write out all of our statements and our reasons and all that, but I'm going to talk through it as if we were doing a full proof. Alright, so here we go. By definition, we know that we have opposite parallel sides, so I'm going to go ahead and I'm going to mark that up. So that and that are parallel, and this are parallel. We're trying to prove that those sides are also congruent. And the way we're going to start that is we're going to draw in a diagonal. It really doesn't matter which one. I'm going to go ahead and I'm going to draw this diagonal into the picture. Alright, now what happens is this acts as a transversal. Okay, we got parallel up here, parallel down here, this acting as a transversal. So therefore angle BAC is congruent to angle DCA by what previous theorem? Let's think about it for a second. Hopefully you thought about the alternate interior angle theorem. Okay, so we have one set of congruent angles. Alright, AC is congruent to itself. Put a mark there. Why is AC congruent to itself? Hopefully you remember the reflexive property of congruence. Okay, next, this angle over here, angle BCA, is congruent to which angle? Hopefully you thought about this angle up here, angle DAC. Why? Why are those angles congruent? Once again, they're alternate interior angles. This time we're just using these parallel lines instead, but you'll notice that they're between the parallel lines. Get the pin out of the way. They're between the parallel lines. Here's my transversal. They're on opposite sides of the transversal, so they are alternate interior angles. Okay. So what do we know about these triangles now? If we look at our order here, we have angle, side, angle, matching up with angle, side, angle. So therefore the triangles are congruent by the angle, side, angle congruence postulates. And if the triangles are congruent, then what's true about AB and CD? AB is congruent to CD because of what? Hopefully you remember this, CPCTC, which stands for, and you can actually, go ahead and talk back to me in the video if you want to, that's fine, but corresponding parts of congruent triangles are congruent. Likewise, AD is congruent to CB, once again because of CPCTC. Alright, so we just proved that if we start with parallel sides, then we can prove that the opposite sides are congruent. That's what Theorem 8.3 says. Alright, Theorem 8.3 says, according to the book, let me see what the book, how they specifically say it, but Theorem 8.3 says, if a quadrilateral is a parallelogram, then its opposite sides are congruent. You could say something like this. In a parallelogram, opposite sides must be congruent. Okay, something along those lines, but definitely you need to know that anytime you have a parallelogram, the opposite sides have to be congruent. So let's come back to this sheet here. Okay, and we're going to add some information to our sides. So B says opposite sides are congruent. Two sets or one set? Well, we just proved that it was true for both sets. So we're going to write down right here B2. Why? Theorem 8.3. Now, you know that I don't like you to memorize theorems by numbers. However, we're going to use the number here. It's shorter. It matches up with what's in our book, and then we can just review it as needed. Okay, let's look at the rest of the sides. All sides are congruent. Well, that's pretty easy to tell by looking at an example of a parallelogram that does not have to be true. It is possible for it to be true, but it just does not have to be true. So we're not even going to bother trying to prove it. Can't do it. Consecutive sides are congruent. Consecutive, remember, means right in a row, in order. So that would mean that this side here would have to be congruent to this side here. That's what consecutive sides mean. Well, that's definitely not true either, so we're not even going to bother to prove it. So we are done with the sides part. So let's move on to angles. Okay, so let's come down to the angles part. Okay, we're going to start filling this in. Let's look at the very first thing that angles says here. Opposite angles are congruent. Two sets or one set. All right, well, let's look over here at this one. This is Theorem 8.4. Okay, Theorem 8.4, we're going to try to prove that the opposite angles of a parallelogram are congruent. Okay, now, we can actually do a lot of the same work we just did. Okay, so if we draw this diagonal in here, we get our parallel lines. By definition, a parallelogram has to have parallel sides. Okay. This is congruent to itself by reflexive property again. Alternate interior angle theorem again. Another alternate interior angle theorem again. Triangles are congruent by angle side angle again. Now, we actually don't technically have to do angle side angle here, because we could just say angle Q is congruent to angle S. And why would angle Q be congruent to angle S in this picture, even without proving the triangles are congruent? See if any of you can remember that. Think back to why would angle Q be congruent to angle S right now, even without proving the triangles are congruent. Hopefully you thought through it and you figured out that we're dealing with the third angle theorem. So angle Q is definitely congruent to angle S. Once again, you could do that by proving the triangles are congruent like we did in the previous theorem. That was a really bad job of making marks. Sorry about that. All right. And then using CPCTC, or like I said, you can use third angles theorem. Now, well, how do I get this bigger version of angle P, angle QPS, congruent to angle SRQ? Well, there's a couple ways you could do it. You could use some angle addition postulate here and here to get two little angles adding together to equal a big angle. And if I'm adding equal things to equal things, I should get equal answers. Or if we were actually going through a proof, that'd be kind of hard to write out. So the other thing we could do, P, Q, R, S, is just draw the other diagonal instead. Okay, if we draw the other diagonal instead, we'd get our alternate interior angles. Get them again. We'd use third angle theorem really fast. Angle P is congruent to angle R. So it's a lot easier to do it that way. All right, so we just proved, theorem 8.4, that both sets of opposite angles have to be congruent. And that's without drawing the diagonal in. We're talking about the whole big angle P, the original angle P and the original angle R. We cannot say something like, angle SPR is congruent to PRS. Those two angles are not considered opposite angles in a parallelogram. Okay, so let's look back at this. Let's look at angles. And right here we have opposite angles are congruent. That's true. We have two sets, so we're just going to write down A2. And our reason for it is theorem 8.4. Okay, let's look at what the next thing says. Angles. Consecutive angles are supplementary. Do we have 4 sets or 2 sets? All right, let's take a look at a picture. All right, so theorem 8.5, got that one down here at the bottom. Okay, consecutive angles are supplementary. All right, there's actually 2 different ways to do this. I'm going to do a proof that's more algebraic, and then I'll also do a more geometric proof. So I'm going to call this X. I don't know what it is. Different than this X. This is more like algebraic X. This is capital letter X. All right, I'm going to call this one Y. Once again, different than this Y down here. All right, now we just proved that the opposite angles are congruent. So X would have to match this. And then Y over here would have to match Y over there. So we have 4 angles, but we really only have 2 letters that we're using to prove that these things, we're going to try to prove that they're supplementary. Okay, when we're talking consecutive angles, we're talking this angle here and this angle here. Or we can talk about this angle here and this angle here. Any 2 angles that are directly in a row, they basically share the same side. Well, we know from our previous lesson, lesson 8.1, that the sum of the interior angles of a polygon is n minus 2 times 180. N is the number of sides. So in this case, 4 sides minus 2 is 2. 2 times 180 is 360. So x plus y plus x plus y equals 360 degrees. If we add together our like terms, we get 2x plus 2y equals 360 degrees. And if we divide everything by 2, we get x plus y equals 180 degrees. So there we go. We just proved that x plus y equals 180. That's the definition of supplementary. So these 2 angles must be supplementary. Here, x plus y equals 180. So these angles must be supplementary. Or here, x plus y equals 180. They must be supplementary. And here, x plus y equals 180, so they must be supplementary. You'll just notice we just made 1, 2, 3, and 4 sets. Okay, so we have 4 sets of consecutive supplementary angles. Now, could we have done that algebraic or geometrically as well instead of algebraically? Yes. I'm going to draw a quick sketch of a parallelogram. All right. If I extend this side and I extend this out and I extend this out, we're talking about these parallel lines here. And we're talking about that angle and that angle. This thing here functioning as a transversal. Hopefully you remember that these 2 angles have a special name. They were called consecutive interior angles. And the consecutive interior angle theorem told us that they were supplementary. So really, this is just the consecutive interior angle theorem. We're just using it kind of inside of parallelograms instead. So does it need a new name? No, not necessarily, but the book chose to call it Theorem 8.5, didn't actually give it a name. All right, and Theorem 8.5 says that we have 4 sets of consecutive supplementary angles. Basically, any set of consecutive angles in a parallelogram are supplementary. So we're going to talk about B here, and we're going to use 4 because we know there's 4 sets. So I'm going to write down B, 4 by Theorem 8.5. All right, let's look at the next couple things for angles, see if they work. All angles are congruent. Well, if we look at our example here, we definitely see that all angles here don't have to be congruent. That one is going to be obtuse, and that one's going to be acute probably. We know that they add to equal 180, but we can come up with all kinds of numbers that add to equal 180 that aren't necessarily congruent. It could be 180, it could be 110 and 70, it could be 152 and 28, could be 90 and 90. all right, but it doesn't have to be. So we're not going to write it down because this does not have to always be true. All right, consecutive angles are congruent. Well, same idea. Could be 180, could be 110 and 70. These do not have to be congruent. Opposite angles have to be congruent, not consecutive angles. Could be 90 and 90 everywhere, all right, but it doesn't have to be, so we're not going to write anything down. So we're ready to move on to the diagonals. Okay, diagonals. Now let's look at the first possibility I have written down here. The diagonals bisect each other. Got to remember what bisect means. Bi, remember, means two. Sect means to cut. So bisect means to cut into two equal pieces. So the question is, do the diagonals actually bisect each other? So let's take a look at another picture here. I've got theorem 8.6. Okay, it's a theorem. We must be able to prove it. Let's go ahead and try to prove that. So if we're going to talk about the diagonals, we got to draw the diagonals. And we're going to draw both of them. So I'm going to draw this in here, and I'm going to draw this in here. I'm going to call this point in here JKLMN, and sounds like a great point to use. All right, so the question is JL being cut in half by KM? And is KM being cut in half by JL? In other words, is JN congruent to NL? Is MN congruent to NK? Once again, we're going to prove this by just proving we have some congruent triangles. So we've already figured out we've got alternate interior angles. We've got some more alternate interior angles up here and down here. We just proved that the opposite sides were congruent in an earlier theorem, so this must be congruent to this. So we've got angle side angle congruent to angle side angle. So triangle, if we do it this way, we'll say JKN. Triangle JKN is congruent to triangle. If I went JKN, I started with a 1 mark, so I got to start down here with LMN. And that was by angle side angle congruence postulate. All right, now, is JN congruent to LN? Well, if it is, they have to be in corresponding positions. So look here, JN, first and last letters. LN, first and last letters. We're good. JN is congruent to LN. Why? Keep in mind, we've learned this before, talked about it numerous times. It's one of those things that's going to show up on your final exam probably. CPCTC. Corresponding parts of congruent triangles are congruent. We proved the triangles were congruent. JN is a corresponding part to LN. Okay, well what about MN and KN? MN is my second and third letter. KN, second and third letter. So MN is congruent to KN, once again by CPCTC. Corresponding parts of congruent triangles are congruent. So what did we just prove? We proved that these things were congruent, and we also proved that these things were congruent. So is this diagonal being cut in half by the other diagonal? Yes. Is this diagonal being cut in half by the other diagonal? Yes, they are both being bisected. Now don't get this confused and think it has to be perpendicular. You can have bisecting without perpendicular bisectors. This is just bisecting. There does not need to be a right angle right here. In a parallelogram that's not a square or a rhombus, which we'll get to later on, this cannot be perpendicular in just a typical parallelogram. Okay, so let's look back over here. Do the diagonals bisect each other? Yes, they do. So we're going to go ahead and we're going to write down A on this sheet right here. All right, so we're down to the diagonal section. So A is true, and that was by theorem 8.6. Okay, well, let's look at the next thing the diagonals talk about. So diagonals are congruent to each other. Okay, so if we look back at this picture, does this whole diagonal here, JL, have to be congruent to KM? No. We can see in this one, this is probably shorter, this is probably longer, but they don't necessarily look like they have to be the same distance. If I take a 2 mark side plus a 2 mark side, it does not have to equal 3 marks plus 3 marks. Now if I could prove that MN was congruent to LN, then that would work, but I have no way to do that. Right? So we cannot prove that the diagonals are congruent to each other. Okay, let's look at the next one. Diagonals are perpendicular to each other. Well, I already talked about that. They definitely do not have to be perpendicular to each other. They might be right angles here in a parallelogram, but it only happens with rhombuses and squares. We're going to talk more about that later on. And then finally, diagonals bisect opposite angles. So what do I mean when I say they bisect the opposite angles? It means when it runs up here into the corner, it cuts this original angle JKL in half. In other words, this has to be congruent to this. Now, that looks like maybe it's true, but maybe not. And we can draw a more exaggerated parallelogram and show you that it's definitely not true. Okay, so let me draw a more exaggerated version of a parallelogram. And when I draw this diagonal, you can tell that this angle down here is definitely different than this angle up here. All right, we would have to prove that this triangle here was congruent to this triangle here, and we're not going to be able to do that. We've got the 2 mark and the 3 mark, so maybe we got, you know, side side, but this does not have to be congruent to this, so we can't get side side side. We don't really have any good reason to say like this angle is congruent to this one. That's actually what we're trying to prove. We don't have any good reason to say this is congruent to this down here, so we can't get an angle. We don't have any good reason to say these 2 angles are congruent. They're a linear pair. That has nothing to do with congruence. So there's no way I can figure out that these angles are being bisected. So that's it for diagonals. There's just one thing. Now if we finally go into the last part, we have a bunch of other stuff, a bunch of area formulas, and then we've got a couple things down here, and I'll tell you these aren't going to show up for a little while. So if you look at these area formulas, the main thing that you need to understand is that anytime you're finding area with any of these things, the things you are multiplying must be perpendicular. So length and width. Well, if we look at a parallelogram, do the length and the width have to be perpendicular? Well, the answer is no. So you can't use that formula. Okay, well what about diagonal 1 times diagonal 2 over 2? Well, once again, the diagonals would have to be perpendicular. And we just talked about why they don't have to be perpendicular right here. So that formula is not going to work. All right, side times side. Well, the sides aren't necessarily perpendicular, so that's not going to work. Base 1, base 2, this one's a little weird, but this basically means you have 2 different bases you're dealing with. Well, we don't. All right, let's go back to the very first one, base times height. Base and height must meet at a right angle. Okay, that's very important. So if we look at a parallelogram, all right, base and height must meet at a right angle. This is my base, and this dotted line that is perpendicular to both things. Okay, let me show you this. Sorry, I didn't have it in the camera view. All right, there we go. So this is my base. This dotted line has to be perpendicular to both parts because they're parallel. Remember, if you got it perpendicular to one, it's going to have to be perpendicular. That right there is my height. Now, a lot of times we'll actually draw it right here instead at one of the corners. That's fine. It's still just got to be perpendicular. Okay, you could draw it over here at the down here, kind of here. Okay, it would have to be perpendicular. Both parts have to be perpendicular here as well. Doesn't matter where you pick. This is the base, this is the height. Now, you can actually do it slightly different. You don't see it done this way quite as much, but you could call this right here the base. And then what would happen is we'd have to have something like this. It's a little hard to draw sideways, but it would kind of go like that. It's got to be perpendicular. And then that dotted line would be the height. Okay, so now all that's really going on when we get something like this is that we've turned our parallelogram this way. So now if you look at it that way, we got the base at the bottom, like what we're used to, and then our height is going up and down. Once again, it's got to be perpendicular to the 2 bases. When I say 2 bases, this base and this base are the exact same distance. Remember, opposite sides of a parallelogram are congruent. Okay, so that's our area formula for a parallelogram. So let's come back over here and let's finish this off. So area, down here in our other section, we're going to use this formula right here. Sorry, I got this zoomed in really far, but area equals base times height. So that's just capital letter A. Now, if you look in your book, the area formulas are not given in the lessons that as we're talking about them, but I do expect you to know them. At the end of this chapter, we're going to have a worksheet that deals with the area formulas. Okay, so we are going to do all of that. All right, let's do a couple quick examples, and then we'll be done with this lesson. Let me zoom out a little bit. All right, so let's start on this one. All right, so I've got this all drawn, A, B, C, D. I got 3 units. That's from A to E. We got an 80-degree angle here, 30 degrees here. I've got an X, which is for EC. Got Z here, got Y here. We're going to solve all those things. So go ahead and copy this down real quick if you need to. Pause the video. Maybe even just try it real quick. This, I hope, is pretty easy. Okay, and then I'll come back and explain it real fast. All right, here we go. So let's start with a Y. Y is pretty easy. Opposite sides of a parallelogram have to be congruent. So Y equals 10 units. It's pretty simple. All right, X, that's a pretty easy one. Diagonals have to bisect each other. They have to cut each other in half. So if AE is 3, then EC must be 3. So X equals 3 units. Okay, Z is a little harder, but not too difficult. we were told that consecutive angles are supplementary. So if this is 80, then that means this whole angle here, this big one, has to be 100 degrees. And if this is 30, angle addition postulate, 30 plus something has to give me 100, then z must equal 70 degrees. Okay, not too difficult. All right, let's make it a tiny bit harder. Okay, go ahead and copy this one down real fast. That's x squared plus 4 and a 12. So I'll let you copy that down. All right, so we know that the diagonals bisect each other, kind of like one of the parts we did before. So x squared plus 4 equals 12. Subtract 4 from both sides, x squared equals 8. X equals the square root of 8, which, if we break that down, you should get 2 root 2. Now, technically, it's not the only answer. Hopefully you kind of think back through algebra class and realize there could be a different answer in algebra, and that's really x could equal negative root 8, or negative 2 root 2. Now, this is a little weird because usually in geometry we don't like negative answers. A negative length doesn't really make sense. But if I take the negative number and square it, it will turn it to positive 8. And positive 8 plus 4 is 12. So x could be either the positive or negative version of this answer in this case, because x is not a side length. X squared plus 4 is. And when I do x squared plus 4, I still get a positive answer no matter which one of these I pick. All right? I've gotten you in the habit of putting units on these things. It may not make sense in this case to put units on a negative distance, so I'm just going to leave it like this, realizing that really it's the x squared plus 4, the whole thing, that gets the unit label. It's the 12 units, not just this, okay? All right, let's come up with this one. All right, go ahead and copy this one down and then try to solve these. All right, so on this one, opposite sides have to be congruent. So 2y plus 10 has to equal 4y plus 4. If I subtract 2y from both sides, I get 10 equals 2y plus 4. If I subtract 4 from both sides, 6 equals 2y, and then divide both sides by 2, and we get y equals 3 units. We can check that real quick. Come back up here. 2 times 3 is 6. 6 plus 10 is 16. 4 times 3 is 12. 12 plus 4 is 16. It makes sense. All right, let's do the other one. 3x minus 1 and x plus 2. Once again, opposite sides have to be congruent. So 3x plus 1 equals x plus 2. We subtract the x. We get 2x plus 1 equals 2. We subtract the 1. 2x equals 1, and we divide by 2, and we get x equals 1/2 unit. Okay, come into this other parallelogram, I'll cover it up briefly. So x equals half a unit. That's a little hard to check, but we'll go ahead and check it. What's 3 times 1/2? Well, it's 3 halves. And 3 halves minus 1, well, 1 is 2 halves, so 3 halves minus 2 halves is 1/2. And then over here, now something seems wrong. 3x plus 1. Oh, well, that's because I completely copied the problem down wrong. Hey, because if I took 1/2 plus 2, I'd get 2.5. Doesn't make any sense, does it? That's why we check our work. All right, once again, maybe I did it on purpose, maybe I didn't. Let's fix that, though. This should be a -1. That should be a -1. That should be a plus. That should be a plus. That should be a 3 now, and then we get a 3 here. Okay, so now x equals 3 halves. 3 times 3 halves is 9 halves. 9 halves minus 1. 1, remember, is 2 halves. 9 halves minus 2 halves is now 7 halves. All right, over here, 3 halves plus 2. 2 is 4 halves. 3 halves plus 4 halves is 7 halves. All right, it's making sense this time. It's why we always check our work. All right, last question. Angles. 2d minus 18. This is a 112. 3e plus 13. Go ahead, copy it down, attempt it, and then we're done. All right, here we go. We know opposite angles have to be congruent, so 3e plus 13 equals 112. We subtract the 13. We get 3e equals 99. Divide by 3, and e equals 33. I'm not going to put a degree symbol on this. There's already a degree symbol right here, so E is just 33. It's definitely not a length, so I'm not going to put units or anything like that. We can check it. 3 times 33 is 99. 99 plus 13 is 112. That makes sense. All right, so how do we do this one? A little bit harder. All right, but keep in mind that consecutive angles are supplementary. So that means that 112 plus 2d minus 18 has to equal 180. If we add these like terms together, we get 2d plus, let's see, 112 minus 18 is 94 equals 180. We subtract 94 from both sides. 2d equals, that looks like 86. Divide by 2, d equals 43. All right, let's check it. 2 times 43 is 86. 86 minus 18. 86 minus 18 is 68. 68 plus 112 is 180. Good. The answer makes sense. All right. So here's what you need to remember. I'll go back to this sheet and kind of talk about it real quick. You need to know the definition. Two sets of opposite parallel sides. It's got to be a quadrilateral, a four-sided figure. Okay, basically a couple examples. Definition tells us that two sets of opposite sides are parallel. This theorem tells us that two sets of opposite sides are congruent. This theorem tells me that two sets of opposite angles are congruent. This theorem tells me that there are four sets of consecutive supplementary angles. We know that the diagonals bisect each other, they cut each other in half, not necessarily at a right angle, but they do cut each other in half, and area is base times height. We need to have all that memorized when we talk about parallelograms. That's the end of our lesson.